Now that we've defined complex function, let's continue playing around with complex functions and let's try to figure out what the definition of a derivative of a complex function would look like. So let's again take inspiration from real-valued calculus and let's try and define the derivative f prime of z, or if you want, you can also write this as df dz. Let's try and define this by again taking the limit of a quotient, differential quotient. So let's say we have a small perturbation delta z which goes towards 0, and we take the limit of the difference of f evaluated at z plus delta z minus f of z, and then we divide that by the difference of the arguments, so z drops out here. This is exactly the same definition as we have for real-valued derivatives. The only thing we've done so far is replacing x by z. So that seems to make a lot of sense. It's very intuitive. Let's now do an example or a small exercise. Pause the video and try to calculate using this definition the derivative of the function f of z is z squared. So what is f prime of z in this case? Pause the video and see if you can recover the result that you intuitively expect. Applying our definition here, f prime of z will be the limit of delta z going towards 0 of our function evaluated at z plus delta z. So that's going to be z plus delta z squared minus the function evaluated at z, that's z squared, dividing this by delta z. This will become the limit of delta z going towards 0 of z squared plus 2z delta z plus delta z squared minus z squared divided by delta z. Fun things happen because z squared cancels here. And now that we've gotten rid of these terms, that means we can also get rid of delta z. So if we divide everything by delta z, then here we have delta z to the power of 1. And if we take the limit, the only thing that's left standing is 2z, which is nothing surprising because it's basically exactly the same definition as we used for real-valued calculus to calculate the derivative of the function x squared. So by now you might wonder, what's the big deal about this complex analysis business? The only thing we seem to have done so far is just replacing x by z, and everything basically stays the same. So what's the big deal here? Well, let's have a look at another example and see what happens there. Pause the video and try to use exactly the same calculation to figure out what the derivative of a second complex function is, namely z multiplied by the complex conjugate of z, so the modulus squared of this complex number. See if you can figure out what the derivative of this function is. Here things start to get a little bit more subtle because we would be tempted to say, okay, f of z, let's have a look at the limit of delta z going towards 0 of our function evaluated at z plus delta z. Now our function is just the modulus squared, right? And then minus the modulus squared of z divided by delta z. Now, it's very easy to realize that the numerator here obviously will always be a real number, that's for sure. In terms of the denominator, yeah, delta z is basically a choice that we can freely make, and it's in essence a complex number. So this complex number could either be a purely imaginary number, a purely real number, or something in between. So this can change, but the only thing that doesn't change is the conclusion that the numerator itself is real valued. So here we would seem to end up in a situation where the result of this limiting operation depends very much on the choice of delta z here, and more specifically, the direction of approach, the orientation of this delta z. Obviously, that's not desired, and we say that in this case, the derivative is not defined, so it doesn't really exist. And that's a bit of a disappointment, obviously. Now the question is, can we figure out when will we be disappointed? In other words, when will we have the situation that a complex function f of z will have a well-defined derivative independent of the direction of approach encoded in this delta z here? And this will be the topic of the next video.